Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Carnot's theorem. Let's begin. The statement of Carnot's theorem: no heat engine working between two given temperatures can be more efficient than reversible heat engine working between the same temperature. Means it tells there will be no such heat engine whose efficiency is much more greater than that of reversible heat engine. Basically, that Carnot's theorem is further named as the efficiency of any reversible heat engine. That is the efficiency of any reversible heat engine. We have to prove how the efficiency of reversible heat engine is more as compared to other heat engines like irreversible heat engines and so on. So, to prove that theorem, we have to consider two heat engine. One is reversible heat engine and another one is irreversible heat engine, and we compare the efficiency of both these two. So, we have to take first reversible heat engine. What happens? We take in reversible heat engine, denoted as R, and another in what happened in irreversible heat engine. Irreversible heat engine, that is denoted by I. So, we have to consider two heat engines, one reversible heat engine and another one is irreversible heat engine, and these two heat engines are working between two temperatures T1 and T2, where T1 is the temperature of source and T2 be the temperature of sink, and we assume that the amount of working substance in these two heat engines is so adjusted, means the work done per cycle is same in both the engines, that is W. So, we have to draw the figures here. In reversible heat engine, what happened? Let that is the source, which is at temperature T1, that is the working substance here. Here is the working substance, and here is the sink. Here is the sink which is at a temperature T2, and in that of reversible case, this is Q1, heat at temperature T2, that is Q2, and the work done, in that sense work done per cycle, that W is equal to Q1 minus Q2. Just I write what happens here. Let Q1 is the amount of heat absorbed by the working substance from that of source at temperature T1 here, and Q2 is the amount of heat rejected to the sink at temperature T2 of that of working substance. So, work done per the cycle is W. Then we can say then W is equal to Q1 minus Q2 in case of reversible heat engine. Therefore, Q2 is equal to Q1 minus W. Therefore, the efficiency of reversible heat engine, therefore, efficiency of reversible heat engine, that is eta R, efficiency of reversible heat engine, that is W divided by Q1, let equation number 1, that is the efficiency of reversible heat engine. Now, what happen in case of irreversible heat engine? Similarly, we take the source which is at a temperature T1, that is source temperature T1, this is the working substance, and sink at a temperature T2, here is the heat Q1 dash, heat Q2 dash, and work done, and the direction of work done by the system will be Q1 dash minus Q2 dash, minus Q2 dash. Here Q1 dash is the amount of heat absorbed from the source at temperature T1, and the Q2 dash is the amount of heat rejected to the sink at the temperature T2, and W is the work done per cycle. Then we can write W is equal to, that is Q1 dash minus Q2 dash. Therefore, Q2 dash is equal to Q1 dash minus W. So, the efficiency of irreversible heat engine, therefore, efficiency of irreversible heat engine that is eta I is equal to W divided by Q1 dash, that is equation number 2. That is the efficiency of reversible heat engine, that is the efficiency of irreversible heat engine. But according to our theorem, according to Carnot's theorem, the efficiency of reversible heat engine is more than comparison to that of any other kind of heat engines. So, let us assume that the irreversible heat engine is more efficient than that of reversible heat engine. So, eta I is greater than eta R. Therefore, eta I, we get the value of eta I here, the efficiency of irreversible heat engine, that is W by Q1 dash greater than eta R, that is efficiency of reversible heat engine, that is W by Q1. W cancel out on each side. So, 1 by Q1 dash is greater than 1 by Q1, taking the cross multiplication here, that is Q1 dash is less than, that is Q1 dash is less than Q1, or Q is greater than Q1 dash, Q is greater than Q1 dash. Hence, the quantity Q minus Q1 dash, the quantity Q minus Q1 dash is positive, that is the positive quantity. Since Q is greater than that of Q1 dash, that is why the subtraction Q minus Q1 dash is positive quantity. So, if we combine these two heat engines, means let two heat engines, reversible heat engine and irreversible heat engines, are coupled together, so that irreversible heat engine works in forward direction and reversible heat engine works in backward direction. What happened? So, coupled these two, let two heat engines are coupled together such that irreversible heat engine I works in forward direction and reversible heat engine R works in reverse direction. So, we have to figure out, show this in a figure. Take that a figure. Here is the source, that is source at temperature T1 and sink at temperature T2, and this is the irreversible heat engine. Here is the reversible heat engine, and the reversible heat engine in reverse direction, that is irreversible heat engine works in forward direction, that is the forward direction. Here is the forward direction, and reversible heat engine works in the backward direction, that is the backward direction, and heat flows like this. This is the flow. Okay. Here is Q1 dash, here is Q2 dash, which is equal to Q1 dash minus W, that is Q2, which is equal to Q1 minus W, this is Q1. So, this is the adjustment of irreversible and reversible heat engine. What is the functioning? So, the irreversible heat engine I takes Q1 dash amount of heat from that of source at temperature T1 and performs a work W, and rejects Q2 dash, that is Q1 dash minus W amount of heat to the sink. At temperature T2. Again, in that of reversible case, that reversible heat engine R takes Q2, that is equal to Q1 minus W amount of heat from that of sink at temperature T2 and performs work W on it and rejects Q1 amount of heat to that of source at temperature T1. In other words, the reversible heat engine works as a refrigerator, and the work done W is supplied by irreversible heat engine I. So, these are the arrangements of reversible heat engine and irreversible heat engine. So, what should be the net heat lost by that of sink? Therefore, the net heat lost by the sink is equal to that is Q2 dash, sorry Q2 right here, that is Q2 minus Q2 dash. In place of Q2 I substitute, that is Q1 minus W, Q1 minus W. In Q2 dash I substitute, that is Q1 dash minus W. So, that is Q1 minus W minus Q1 dash plus W. W cancel out, which is Q1 minus Q1 dash, which is the positive quantity, as we before discuss. Q minus Q1 dash, that is the positive quantity. Here is the, that is also positive quantity. positive quantity. Look that one. In other words, Q1 minus Q1 dash, amount of heat is transferred from the sink to the source without the help of any external agency in that of case, which is not allowed by the second law of thermodynamics. So, what I write here, what is that meaning? In other words, we can say Q1 minus Q1 dash, amount of heat is transferred from the sink to the source without the help of any external agency. Which is not allowed by the second law of thermodynamics. Which is not allowed by the second law of thermodynamics. Means it contradicts to the second law of thermodynamics. As a result, which gives rise to the assumption we take as eta I is greater than eta R, and the efficiency of irreversible heat engine is greater than that of reversible heat engine is wrong. So, therefore, it results finally we get that a reversible heat engine is always more efficient than an irreversible heat engine working between the same temperatures. This is the Carnot's theorem, means the efficiency of reversible heat engine. So, with the help of this visual lecture, we understand what is Carnot's theorem and its proof of that Carnot's theorem by taking reversible heat engine and irreversible heat engine. We found out its efficiency and compare its efficiency. First we assume that is greater than from that, and proceeding like this, and finally we get the assumption is wrong. That is why we say a reversible heat engine is always more efficient than that of irreversible heat engine working between that of same temperature, which is known as the Carnot's theorem regarding the efficiency of any reversible heat engine. So, with this useful and informative notes, let me wind up this session. Thank you.